Okay, so we have now learned how to draw ionic bonds showing the valence electrons being transferred from one element to another element until they both satisfy the octet rule. We've then seen how we can use that to find the formulas of the elements. And that's great, but sometimes it takes a long time. So today what we're basically going to be discussing is how to do a shortcut on this. So I'm going to start by looking at the periodic table itself. One thing to note about ionic compounds is in order for them to work, and hopefully this is something you realized, you have to have one atom that wants to lose electrons and one atom that wants to gain electrons. So with that in mind, I'm going to take a look here at the periodic table, and over kind of on the right side, we've got what we call this staircase. This staircase separates the metals, which are on the left side of the periodic table, those are the metals, from the non-metals, which are on the right side of the periodic table. So the basic idea for ionic bonding is that in order for an ionic bond to form, you have to have one metal and one non-metal. One quick thing to point out, even though hydrogen is over on the left side of the periodic table, it is actually a non-metal, but we're not going to focus too much on that right now. So if you were to have to figure out, can two elements form an ionic compound? Basically, you're just looking to see, do you have one element on each side of the staircase? For example, calcium is a metal. It's on the left side of the staircase. It has 2 valence electrons because it's in group 2A, so it's going to want to lose electrons. On the other hand, fluorine over on the right side is a nonmetal. It has 7 valence electrons, so it's going to want to gain. So calcium and fluorine could, in fact, form an ionic compound. Another example of something that could form an ionic compound would be iron, which is a metal on the left side of the periodic table, and phosphorus, which is a nonmetal on the right side of the periodic table. So basically, again, you're just looking at this staircase. If you have one element on the left side of it and one on the right side, we will generally say that is something that could form an ionic compound. Another little thing we're going to go through here is finding shortcuts on those charges that the atoms are going to obtain once they've formed an ionic compound. So we've gone through and we've looked at how many valence electrons atoms have and if they gain and lose and what their charges will become. And there's basically a pattern to this. So starting in group 1A on the periodic table right here, we know that all of these atoms have 1 valence electron, 1 dot. So we know that in order to satisfy the octet rule in an ionic compound, they are all going to lose 1 electron. Remember, when you lose an electron, your charge becomes positive. So up at the top of that group, I'm writing +1. That just tells me that all of those elements in an ionic compound are going to have a charge of +1. So if I want to know what the charge of cesium is, I can go through and I can figure it out, or I could just look at the periodic table, go up to the top and go, oh, okay, yeah, cesium has a charge of +1. Again, it's important that we understand how we got there, but so that we don't have to take so much time in the future, this is just a shortcut. Same idea with group 2A. All of the elements in group 2A have 2 valence electrons. 2 valence electrons, 2 valence electrons. So they are going to lose those 2 valence electrons, and all of their charges are going to be +2. So at the top of group 2A, I'm just putting the charge +2. For group 3A, they have 3 valence electrons, 3 valence electrons. So again, they're going to lose those 3, and their charge is going to become +3. Hopefully you're seeing this pattern here. We're going to skip group 4A because typically that's not going to be part of an ionic bond anyway. Group 5A, those have 5 valence electrons. Remember, the most electrons an atom's going to gain or lose is 3. So it can't lose 5. The other thing it's going to be able to do is it's going to gain 3. So when you gain 3 electrons, the charge becomes -3. So all the elements in group 5A have a charge of -3. Group 6A, those have 6 valence electrons, all of them in there. So they are going to gain 2 to get 8, and their charges will be -2. And then finally, group 7A, they've got their 7 valence electrons. 7. They just need to gain 1 more. So when they gain 1, their charge will be -1. So again, this makes it easy to find the charge of an element with honestly not having to think too much about it. I could just find the element. So if I'm looking for the charge of bromine, I could find it on the periodic table. I can go up to where I've written my charges, and I see that the charge of bromine is going to be -1. So little shortcut there. The last shortcut is going to involve actually finding the formulas of our ionic compounds. So again, we've gone through, we've drawn the dots and the arrows, and we've used that to find the charges, but again, that takes a long time. So one thing that I want to point out that's important for this shortcut is that we will notice that the charge overall of positive ions and negative ions end up canceling each other out in an ionic compound. What I mean by that is as follows. So for the magnesium atom in this first problem here, we've got one of them, and its charge is +2, a total of +2. For the chlorine, we have two of them. Chlorine. Each of them has a charge of -1. So the total positive charge here is +2, and the total negative charge, if we add those up, is -2. So we have +2 and we have -2, and those cancel each other out. So altogether, this ionic compound is neutral. It does not have an overall charge because the positive and negatives cancel each other out. Let me give another example of that. Let's go to this one. So in this one, we have two potassiums. Each of the potassium has a charge of +1. So the total positive charge is +2. We have one oxygen, and its charge is -2. So the total negative charge is -2. So again, the +2 and the -2 cancel each other out, and the overall charge of the compound is neutral. One more example of that with one of the more kind of complicated ones. For this one down here, we have 3 berylliums. We could see that in our formula. So each of them has a charge of +2. If we add all that together, the total positive charge is +6. And then we have 2 nitrogens. Each of them has a charge of -3. If we add those together, we get a charge of -6. So again, the positives and the negatives cancel each other out. And using that concept and understanding that the idea behind it is canceling out the charges, we can do something called the crisscross rule. And it's something that works because the charges cancel out. And the crisscross rule looks like this. So I have my compound magnesium and chlorine, magnesium chloride. Again. All right, so the way that I'm going to do this is I'm going to find the charges of each of my elements that I'm working with here. So magnesium has a charge of +2, and chlorine has a charge of -1. Now, our overall idea here, again, is that we're going to have to cancel out our charges in an ionic compound because the overall ionic compound has to be neutral. Now, we could think about this in terms of math, but as an even bigger shortcut, we can do something called the crisscross rule. And basically it works like this. If I want to know how many magnesiums there's going to be, I look at the number associated with chlorine, which is 1, and I crisscross. In my formula, I'm going to have 1 chlorine. If I want to know how many chlorines there's going to be, I look at the number associated with magnesium, which is 2, and I crisscross. So I'm going to have 2 chlorines. Now remember, we don't typically write the 1. So we just assume it's there. So my overall formula would be MgCl2. I can double check that with what I already have from when we did this assignment before. And that's right, MgCl2. That's a crisscross rule. So I'll show that again. If I'm looking at beryllium and nitrogen, I can find those on the periodic table. So beryllium's right here, its charge is +2. Nitrogen is right here, its charge is -3. So +2 and -3, I'm going to get that out of the way. So I've got beryllium with its charge of +2, and I've got nitrogen with its charge of -3. And now I can do the crisscross rule. If I want to know how many berylliums there's going to be, I look at the number associated with nitrogen, which is 3. Now, important to note, you're never going to put pluses or minuses in your formula because the formula tells you how many of each atom there is. You can't have a -3 amount of berylliums. That doesn't make sense. So we're just putting the number. If I want to know how many nitrogens there are, I'm going to look at the number associated with beryllium, which is 2. So it's going to be N2. So again, we are crisscrossing here. This is the crisscross rule. I double check. Does that match up with what I did the other day? Yep, they're both BE3N2, so the crisscross rule works. The one exception to the crisscross rule that is important is when the charges are equal to each other. And what I mean by that is magnesium, if I were to look at the periodic table, its charge is +2. Sulfur, its charge is -2. When the charges are equal to each other like that, we just cancel them out and we just have one of each element. If you were to write Mg2S2, that would be incorrect. You have to cancel it out, so it's just Mgs. We can look back at our diagram and we could see we only need one magnesium and one sulfur. So that is how we do the crisscross rule. So now looking at the Ionic Formulas worksheet, we're gonna do the same thing here. We're gonna look at our elements on the periodic table. So we've got sodium. If you were to look on the periodic table, you would see that sodium has a charge of +1. We've got chloride, which if we remember the ending has been changed, that's actually chlorine. Chlorine has a charge of -1. Now this is an easy one. The charges are the same, so they just cancel out and it's NaCl. For the next problem, aluminum chloride. If you look on the periodic table, aluminum has a charge of +3, chlorine has a charge of -1. So to do this one, we are going to crisscross. When I want to know how many aluminums there are, I'm going to look at the number associated with chlorine, which is just 1. So there's 1 aluminum. If you want to write the 1, that's okay. You're technically not supposed to, but for me it's okay. But we're going to leave that just as Al to show that there's 1 aluminum. And then to know how many chlorines there are, I'm going to look at the charge associated with aluminum, which is 3. So the formula would be AlCl3. We'll do one more of these. Let's look at strontium nitride a little bit further down. Strontium has a charge of +2 on the periodic table. Nitrogen is -3, so when we crisscross, if I want to know how many strontiums there are, I look at the number associated with nitrogen, which is 3. If I want to know how many nitrogens there are, I look at the number associated with strontium, which is 2. And that is our shortcut, the crisscross.